Hello everyone. We are going to start the session. So this is Praveen from Infini, your session coordinator. And I welcome you all for joining the live and interactive session on artificial intelligence with a focus on deep learning. A brief about Infini would like to share is that we are a team of young professionals from IT industry background, experiences who have come together to bridge the learners and industry experts, bringing them on a single platform where the experts can share their on-the-job experience and knowledge through our Infini platform. I would also like to introduce our lead instructor for the course, Dr. Aditya Nigam, who is based from India and is currently working in IIT Mandi as an assistant professor. He is also involved in research activities in the subject, which he is going to teach, and you all will be knowing more of it during the course session. We shall share with you on your email the Infini dashboard guide for the features available on the Infini dashboard, and also our support email ID, whereby you can send any queries you have regarding Infini platform on that email ID. Before we start the session, just want to inform all the participants that if during the session, if for any queries related to Infini, they can raise their queries by clicking the chat button, which is available below on your screen, and send it to me through chat text, or also they can raise a query by voice by unmuting the mic icon. Similarly, for any technical queries related to the course topics can be raised to Dr. Aditya Nigam. So now I request Dr. Aditya Nigam to take it forward and hope you all have a good time learning. Thank you. This is you can take it forward.
Okay, thank you very much. So, so before going to start the session, as anyways also being written that I would like to introduce myself. My name is Aditya Nigam and I'm a faculty member here at IIT Mandi. I'm teaching for something like 5 years around, and from the last 2 to 3 years I'm teaching this course of deep learning over here. And my area of interest, or if I say that my area of research, is actually in applications of these machine learning and artificial intelligence systems for coming up with things like biometric authentication. So it's like face recognition, fingerprint recognition, iris based authentication, and things like this. Along with that, we have also started working on many areas which are closely related to medical imaging. So given MRI, different analysis that one can do, given CT scans, what one can do. So MRI and CT scan, these are the two modalities right now in which we are interested. We also have started to work on a very recent upcoming trade, which is called as diffusion tensor imaging. So in that area, we are also doing something. So most of my work is actually centered around these things, but I used to design deep learning architectures, how to train them, how to design them to somehow solve different types of problems, which are right now in these different fields. Along with this, is also being said that some introduction of individual students is also going to happen. So may I request all of you to unmute one by one, or maybe someone can coordinate, like Manoj is there, or somebody can coordinate, and one by one students can give say something about themselves and their background. Can we start?
Praveen, I think you can coordinate, I would say. I think this will give an idea about Adit sir students level. So if few people even they can introduce, that will help overall session.
Hey, this is Vijay Srinivasan. I'm working as a networks architect, and I joined this course to understand the basics of AI and deep learning and try to get involved more into that space. So yeah, I'm joining from US.
Okay. One more thing is that what is your background? I mean, you are an engineer. What type of degree that you have?
I'm basically a mechanical engineer.
Mechanical engineer. Okay, good.
Yeah.
Thank you.
Yeah, hi, this is Rajesh Nichanametla, and my background is on Masters in Computer Applications.
Okay.
And also I'm working mainly on data warehousing tools, and particularly I'm looking on this course like advancement on my career, and also learn more on artificial intelligence and machine learning. So where I can implement those ones in cloud computing and also like on data warehousing area.
Great. Thank you.
Thank you.
Hi, everyone. My name is Sai Rachkunda. Currently, I'm a biochemistry and CS student here in US. I'm taking this course to get an introduction to AI and deep learning so I can apply into some of the research I'm doing currently.
Okay. Thank you. Anyone else who is going to say?
Hi, this is Anil Nichanametla. So I am from Detroit. I work in Java technologies. So I want to see if I can learn artificial intelligence and see if I can apply this to my career side. So,
oh, that's good. Great, thank you.
Hi, this is Siva from Detroit. I've been working in database technologies and working as a data visualization expert for now.
Okay.
Thank you.
Thank you.
This is David from London. I work for an investment bank over here in design and development. Recently, there been some about using artificial intelligence for automation and some stuff like that. So just keen about.
Yeah, that's good. So you work in a bank, as you have said.
Yes, what is in the development.
Okay. Thank you.
Good afternoon. My name is Amar. I'm an engineer by background in electronics and communication, and I have been in the industry for quite a few years, predominantly in management. Right now, I work for Microsoft.
Okay, good. Thank you. Anyone else?
Hi, this is Swapnil.
Yeah.
I am from Durg, Chhattisgarh, and I belong to the education industry.
Okay. And what's your background?
I am an IT graduate.
IT graduate. Okay.
Yeah.
Good. Anyone else who want to say anything? Are we done? Because there are few more. So in between, if you wanted to say anything, then you can always unmute your mouth, this mic, and you can talk. And during this class, probably you can mute your mic, and whenever you want, then you can always talk directly to me. Chats may be slightly difficult for me, so my suggestion will be that in between, whenever you have any question you want to say, unmute yourself and say whatever you want to know about that. So that's great. We have got some introduction, and with this we are going to start our first module, and let us see that what are the things that we can cover up, and we all can understand that it's actually a very varied audience. So I welcome all of you. Let's start about this deep learning. So this course is mostly going to talk about a very upcoming emerging, if I say that a technology that is being used for so many different available applications. And this technology is actually deep learning. It's an extension of, you can say, or if I say that's actually a part of different machine learning algorithms. And if I say that AI can actually be seen as a very big umbrella. Under that, we have a small area which is actually called as machine learning. And under this machine learning, we have so many different types of algorithms by which we can learn. We can let a machine to learn, and do things as a human can do different types of learning. And once you learn anything, then you can start to use that knowledge to solve different types of problems. So out of so many different algorithms which are being present in machine learning, deep learning is neural network is actually one of them, and the extension of neural network is actually deep learning. So let's start with this, that making smart algorithms that can that can efficiently and effectively perform a particular task. Efficiently and effectively, both of these things are important, because we do not want algorithm that's going to take huge amount of time to solve the thing, as well as we want an algorithm which is very accurate. So effective as well as efficient, both of these things are very important if you wanted to come up with something by which you can do something important. According to this definition of artificial intelligence, slightly different than whatever is being written most of the places. If I say that artificial intelligence, it's actually wanted to say that we wanted to train a machine artificially to perform a certain task. So we have some sort of machine or some resource that we have, and also we have a task that we want our machine to somehow learn. And once it actually learns that, then we will say that the intelligence is that the ability that we have got, how one can apply our knowledge to solve different things. So if I wanted to say that we wanted to come up with a machine that can understand how to do a task, and then that knowledge, whatever in order to perform that task, whatever the knowledge it actually acquires, what is a way by which we can use it to solve different applications. So overall, this is going to be the goal of our whole course, that given given such type of machines, or given such type of algorithms by which you can let some machine to perform some task which requires certain type of knowledge and intelligence, this is the thing that we wanted to see, that how we can do that. And for that we are going to use the neural networks and its extended version, which is actually called as deep learning. So let us start with the first problem that we used to face whenever we wanted to solve any type of problem, which actually mean that this problem is actually classification problem. And in machine learning, we are going to always encounter two types of problems which are going to be there. First one is classification, and other one is regression. So suppose that we have we have cat and dog. I mean, we have cat images and dog images, and maybe we have real cats and real dogs. But right now I'm talking about, say, some cat images and dog images. And given given any such type of images, if you wanted to come up with any algorithm, if we show this algorithm too many different types of cats and dogs, then we wanted to say, given these cats and dogs, we wanted to understand that given this image is a cat or a dog, we want to see that our algorithm is able to understand and differentiate between cat and the dog images. So the point here is that so suppose that if you have really an image like this, in which we have suppose that it's a 100 cross 100 image. So we are actually having 10 square, I'm sorry, 10 power 4. This many number of pixels, given such 10 power 4, 10,000 pixels, maybe even more than that. So this is actually 10,000. 10,000 pixels, if I give you, can you really tell me that whether this 10,000 pixels belongs to a cat or to a dog? So the point is that literally we have huge amount of data within any given data point. Suppose that it's an image. My image is right now a single data point. Given this single data point, which is actually 10 power 4 different values, we wanted to see that so how can you represent such 10 to power 4 different values? And if you can somehow represent it in some form, say R, some type of form R, if you know this R, which essentially mean that I am having such a high dimensional space in which our image is actually there. So if our image is having such huge amount of information, do all of these information is important, relevant or not? So I will say that literally we can have infinite amount of infinite, or one can say given an image, we are having a finite amount of information, but essentially it's having huge amount of information within an image. And all of these images, all of these information is not most of the time relevant. We have to somehow actually come up with a way by which we can extract this useful or the meaningful information that we used to call as the signature of that image. Assume and suppose that we somehow got a way by which I can convert our this 10 to power 4 values into some 128 dimensional vector, say x1 x2 to xn, and this n is here actually equal to 128. If somebody knows how we can have 128 such things, then this 128 such things would only be using this 128 such values that we have somehow taken, extracted from a cat or any cat image, and use that information to differentiate between a cat and a dog. But what should have to be these 128 different values? That's going to be very important. There has to be someone who is really very expert to really extract these 128 features in such a way so that whatever image that you are going to give me, I can extract this 128 values. And just think about that 128 dimensional space. In that 128 dimensional space, individual these one cat or a dog, this 128 dimensional vector can actually be seen as a point. These are the different data points that we are going to have, and this can actually be said as the features that we have extracted from our real data. So what features one should have to extract? So for that we have to see that what is the thing that you wanted to do, what is your objective function. Depending upon your objective function, which is right now we wanted to differentiate between cat and a dog, so we will have to somehow ask things which can differentiate between cat and a dog. So 128 dimensional values or 128 different values one should have to be asking or extracting from our real data in such a way so that if we see one in that 128 dimensional space, if we see these images, the cat images and the dog images should be completely different. They should have to be seen in two such type of two one can say that they can be in two different sides, and probably you can come up with a line like this line we used to say most of the time as a classification boundary. We actually wanted to come up with this type of classification boundary, and this classification boundary is going to tell that if we have this neat and clean boundary like this, then very easily you can say what are the points which are to my left and the points which are to my right. They both are going to left points are going to be say in the category cat and the right points are going to be in the category dog. So this is actually the classification problem that we wanted to solve, which means that if I give you all these points and these representations, can you come up with a way by which you can give me the equation of this classification boundary? And suppose that it's actually a two-dimensional space, then the equation of this classification boundary is very simple for us, that we all know that a1x plus a2y is equal to say a0 or something like this. That's an equation, linear equation, which is actually said as the equation of that line. If it is not two-dimensional space, then it may be, if it's a 3D space, then in 3D space we are trying to come up with a hyperplane. In 4D space we wanted to, so in 3D space we used to say it as a plane, but if it is four dimension or 5 dimension, anything which is more than 3, that is being called as the hyperplane. So our problem is that we wanted to learn such hyperplanes. We wanted to learn such hyperplanes that can separate two classes with minimum error over the given data set. So minimum error means that if I have a point which is actually a blue point and it got something over here, this got misclassified. So we wanted to reduce the misclassification as much as possible. So So this is actually the background of the classification. And with this, let us see that whatever the big advancement which are being done in this area of deep learning, and then we will start formally about talking about this deep learning. So right now you can see that few faces are being there. If I say that you have to match this face with this face, so it's literally not possible, because the area with the both of these images are showing two different things. And this area, in fact this part is actually not being shown over here, so how you can even match? So there are ways by which they have shown that, from this image, from image number, from the front, the profile face, you can turn it into images like this, and now you can match these two images. So you can see that this is being done using deep learning. So the things which is not even present, invisible things, it's actually generate new things for you. These are the GANs. We will talk about this later, but this is a most preliminary work. If you wanted to do, that's the object detection. Any computer vision thing that you wanted to do, so you will have to have some way by which, if I show you multiple images, so in that somebody has to say that, okay, this is the area, and this is actually banana, this is actually orange, this is different types of fruits which are being there. And even you can now count that there are 4 oranges and 1 banana. Here you can say that this is my TV monitor, this is a TV monitor, this is something, some animal which is being there, domestic cat is there. So object detection is very, very important, and these are some of the networks. We'll try to see some of these networks in detail, that how they actually try to do this type of stuff, trying to come up with the different bounding boxes that are saying that they are having a different object inside it. Automatic colorization essentially mean to say that I convert this image to directly this image. I will automatically colorize the things. So if I have image like this, I will convert it into this images like this. So you can say that image like this can actually be converted into an artificially colored image automatically. Denoising means to say that, and all these things are being done using different different deep learning algorithms. Denoising is there are multiple networks which are now being proposed that can do denoising. So it will take images like this and convert it into images like this. So it can easily remove the noises. If this super resolution says that I have an image like this, if you see that the image like this, and given such image, if I take this part and zoom it, in that image it is not possible to see, but if I do super resolution, I can find out the what is being there. So there are multiple algorithms by which they are going to do this super resolution very well. This algorithm is actually the image inpainting. So image inpainting means that I am having a image like this, and in that this part is actually not there, it's occluded or not there. I directly somehow regenerate that part for you. So parts which are not there, they can actually be generated. Here you can see that this part was not here, and it's actually being generated here. So you can understand that there was actually hotel, but it's not able to understand that there has to be HOTEL, but it can make something which is very similar to the patches which are adjacent to this patch, and ultimately you will not be able to really know that that part was not present. There is a artistic style transfer. This is a very new problem, in which they used to say that I wanted to convert this Mona Lisa image into different types of available artistic um, um, available artwork. So if you wanted to convert Mona Lisa into this thing, then artistic style transfer is actually being possible. Here you can see, something very interesting, that if I show you an image like this and an image like this, now you see that it actually have the content of this, but the design of this. So these things are also being done using deep learning algorithms. This is a very recent work in which you take an image like this, and this is input number 1 and the input number 2. This is a reconstructed image using a deep generative adversarial network that we will somehow see at some point of time. And it's actually doing what? It's actually taking the content of image 1 and the style of image B. And this is the content of B, but the style of A. So all these things are actually being possible. Here you see that this is image number 1, and this is image number 2. The third image is actually having the content of first, but the style of second. So these the amazing things are actually being done. This semantic style transfer means that I will just only draw these doodles for you. Given such doodles, I will generate images for you, neat and clean images. Image to image translation, for this several deep learning architectures are being proposed, in which you can see that given such input in which just only the outline of a bag is being given, I can convert it into bag like this. I will convert from black and white to the color. I can convert day to night, night to day. I can convert satellite image into the map. I can convert segmented image into a real scene. I can convert into input, which is something like this, into directly into a input like this. I can change the color of this. I can change the design and the texture of the object that you wanted to generate. You give me input like this, I can generate different types of shoes for you, which are not available. They are not present physically, but I can make things for you. And if you like that, then only we are going to, then only it's going to be, you know, if you like, you purchase, and then that thing is going to be produced for you. I can change the color very easily. As anyone knows that color can very easily be changed, but I can change so many things in that design itself. Then it comes that suppose that is it possible if I give you a horse image like this, that can directly be converted into zebra. So this type of work is actually being done in very recent paper, which are actually called as cycle GANs, and these GANs we are also going to talk about, in which you can see that how precisely this algorithm really understand that what are the places where there is actually a horse. It will first understand that there is a horse. Once it understands that there is a horse, it convert only this region it's in such a way so that it becomes a zebra. Not only here, it can convert summer to winter, winter to summer. It can convert monet to photos and different all possible combinations. This was the image to image synthesis, and then it comes on to the text to image. It's in this new papers, which actually called as the stack GAN and then attention GANs. So they say that I am now only going to give you the input as my input is now this. The bird has a yellow belly and torus gray and wings and throats and naps. And then you can see that this is the output that's going to give you. So this is amazing stuff which is happening, in which you are just giving the text as an input, and output can be, you know, images which are going to have things like this. And here there's the attention GAN, that is a very latest paper, maybe last year's paper or last year paper, in which they have said that the text, that's the input text, is the bird. So you can see that the input text is the bird has yellow crown and a black earring, and that is round. So you see that the type of image which is being generated is really very good, and really matches to the text that's being actually given to us. This bird is not real, it don't exist, but you can see that how clearly these deep learning algorithms are solving such complex and complicated problems. New papers are also being there. So this is the basic introduction, that what a deep learning algorithm can do for you. If you have any question, then you can ask, then we can move into other direction. Anyone wanted to ask any question, please ask.
Yeah. Hi, this is Rajesh.
Yes.
Hi, yeah. I have one question. Like, as we are in IT industry background, so
yes,
how does it will help us? Like, because the examples whatever I have shown all are like
yes,
related to the image, or to find out the image, to find out all the details of the other things.
yes.
But how does it help us in IT industry? So if you have any example, that will be very helpful for us.
I can give you. Can you tell me that what is your work, what you usually do?
I work on financial background, like particularly banking and insurance.
Okay.
But mainly my background is on data warehousing, as I said, like business, like solution architect, like
Solution
BI
architect.
architect. Yeah.
Yes. That's understand. So let us talk about this banking and insurance. This banking and insurance, it's actually wanted to learn so many different things about their customers. If you have huge amount of customers, that we usually talk about this, that you wanted to give loans. You wanted to give loans and you wanted to check that whether this guy is going to return us or not, what type of customer this guy is. So if you can track the history of a customer, you can somehow wanted to understand that what type of behavior that loan submission return loan submission patterns that you can get. Similarly, in the type of insurance, probably you wanted to know. So suppose that your customer is a data. My customer is the data, and for each of my customer, I'm asking x1, x2, x3, basically some 10 different question. What is your age? What is your profession? And what is your salary? What is your demography? What is your background? Are you engineer, doctor? Think there's some multiple several things that you have asked. Given this, so now just see that this is actually a feature vector, that feature vector of a customer. So now I am having, say, 10k different customers. So for every customer I am having x1, x2 to x10 different things, and this is my customer number 1, and then I have customer number 2, like this. Now given all of them, if you somehow know that the labels for them, I'm converting it into a supervised problem in which the labels are like that. He was a defaulter, he was not a defaulter, he was working very well, he is an excellent customer, he is a very poor customer. Things like this, if you have labels like this, we can train different algorithms which can understand the behavior of a customer. It can understand whether loan has to be given, whether loan is not required to be given to this guy. Insurance, similar things are being there. Insurance also, now the companies actually wanted to know the health of a person. So suppose that I am having a customer and this is its previous data history, that he is having a what is the quality of his heart, he is having some heart trouble or not, what is the quality of its lung, whether it is having good lungs or not, he is a smoker or he is not a smoker. So many different things that you can ask for every of your insurance customer, and then you decide that what type of insurance that this guy requires or this guy can be given. So if you have good amount of such data, these all things are actually being can be predicted. So you can talk about this, but the only thing is that these are different vectors. I was talking about different images. If it is actually vector, then we require fully connected networks. And if there is any type of time series dependency, which means that suppose that you are talking about some stock prediction, in which I say that my stock is X, and right now it is X1, next day the value is X2, third day the value is X3. So there is actually some dependence between the previous things. If there is some dependence like this, then we require another type of network that is called as recurrent neural network. So all these things we are going to see. This is fully connected networks. We will see this in first, recurrent connections. We will also see this thing. In between, we are going to see that the CNNs that are actually working over the images that I have shown. So this is a fully connected, this is the convolutional neural network, RNN, recurrent neural networks, and using all of them, we may be talking about GANs, that are the generative adversarial networks. So in each and every place, wherever we are interested, I can assure you that in whatever area you are working on or you want, there are going to be deep learning algorithms which are solving problems.
Got it. Thanks, Aditya.
Aditya, this is Vijay.
Yes.
What kind of statistical knowledge do we need to have to understand all these algorithms to apply that to what we do?
Yes, so Vijay, you have asked a very interesting question. I will say that it depends upon, so you have asked two things. I mean, statistical knowledge and then application. So that's why I'm saying that statistical knowledge and then application. So if you only wanted to understand how to apply these things, you do not require a very heavy set of statistical knowledge. Only application requires some amount of statistical knowledge that can easily be imparted to anyone during the course. But suppose that you are really interested to build such big high-end system and try to come up with a big research problem and want to solve that, then huge amount of statistical knowledge is required. And only point is that if during this process of our this course, we are interested right now to somehow understand the some initial basic statistical knowledge that I will tell you in between whenever it is required. Sometimes so two small things which are being required. First one is the small basics of linear algebra and some probability analysis. So from some linear algebra and some probability, we can definitely understand why they are working and how they can be applied to different areas. If you want more than this, then you require huge amount of LA and probabilities.
Okay. Is there any prerequisite, like should we do any homework offline
yes, so
to come up with this? Okay.
Yes, so we will. I will let you know that what are the basics that are being required. But essentially, I initially understand. I wanted to say that everyone will be able to understand. I should have to be, able to understand that if it's an n cross n, and if suppose that this is n cross 1, then you are going to get something which is actually n cross 1, and it's actually a linear system of equations. And how to solve such type of linear system of equations and the visualization of that. So if this is okay, along with this, I require x, which is actually a random variable, and this random variable and the meaning of this random variable. So these two things, if we know, then we can start. In between, we require certain more things. We will somehow try to fill whenever it is required, but basic mathematics is anyways is essentially required. Linear algebra and probability, maybe first 2 chapters they are being required, that I will not be covering. So in between I will tell you.
Sounds good. Thank you.
Okay. Anyone else wanted to say anything?
Hi Aditya, this is Anil.
Yes.
So
Yes.
one question I have is, so our course goal is to know for scenarios which algorithm to apply, or will you also be telling us like why this algorithm is being used and go and modify the existing algorithms, or to apply to write new algorithms totally? So how is it like?
I can tell you that writing new algorithms, you require huge amount of efforts. That course that I am going to cover right now, I'm also teaching here in IIT Mandi this course of deep learning, and it's actually 42-hour course. So right now we are only offering it for a given amount, a limited amount of time. So in that, our goal is in-depth understanding of few things, in-depth understanding of few networks. So definitely few networks everyone will be able to understand. It's not going to be a black box. If I say that this is my object detection, you take this thing, give it an image, and the output image is going to have bounding boxes like this. No. That is not the thing that I'm going to tell you. I am going to tell you that how this algorithm is working, why this algorithm is working, and if you wanted to change this algorithm, what are the changes that you can introduce. But along with that, if you wanted to really come up with new things, then you require good amount of background, which is as it's been said, the statistical knowledge. Along with that, you require linear algebra, probability.
Correct. So for example, like now Ola cab rides, these are there. So
yes,
we will be getting an example of which algorithms to use to choose where the most probability of getting a ride request to the Ola or someone, right? So
yes.
those kind of predictions we can do, and what parameters to apply, and which algorithms to use, those we will be knowing it, right?
Yes, I'm sure that once you complete this course, then you will be able to see the problem, and anyways you will directly understand that what type of model is required to solve such problems.
Okay, thank you.
Yeah. Anyone else?
Hi, I have a question. So
Yes.
a lot of the examples you showed, there were 2D image conversions. So,
Yes.
like in medical field, you have MRI, CAT scan, PET scan. So these are 3D. So you have overlay of thousands of images, 2D. So
Yes.
in current AI deep learning research, is there algorithms that go, like they'll compile, hundreds of thousands of 2D images to construct like a 3D set of predictions?
Yes. So as you have said, definitely. So we will be working on 3D images as well as, it's 3D stack of images. In fact, you can say it as images like this, and we will be working on videos as well. So both of these things we are going to see.
Okay, thank you.
Okay. Anyone else who want to say?
So can you give an example how this is applied to auto industry, like manufacturing?
Auto manufacturing.
Yeah.
So auto manufacturing, because I'm also not very sure. So can you tell me that in auto manufacturing what you used to do? Then I can give some example.
So manufacturers sell stars, right? So every year, like there should be some prediction about what cars, kind of cars users is looking at, or are they looking at SUVs, or how to predict uh, the sales going to be for next year, or something like that. Like
Okay, yes. Yes, so in that case, let us see that suppose that I am having some customer. As I have said that in all these business models, whatever the business you are looking for, maybe for medical insurance, maybe for banking, maybe for selling some product. So you are going to have some customers. Depending upon your product that you wanted to sell, you need to ask some proper questions, and the answer that each of these customer, suppose that any customer CI, this CI customer is going to give different types of answers. And what are your questions? Questions are going to be X1, X2, X3, and some n different questions. We need to design these questions as well as possible so as to somehow find out that is going to be helpful for your final objective of prediction. Suppose that you wanted to find out that a new car that you are going to launch, suppose that this is my new car model number A. You want to somehow know that whether it's going to be a hit or a miss. So you need to ask these customer that what type of engine you are looking for, what type of top speed you are looking for, what type of cost you are looking for, what type of durability you are looking for, and different questions. So these questions have to be somehow designed by the domain expert. But when you ask these things, not just see that one customer, this single customer is actually being converted into a feature vector. This vector is nothing but the answers of all the questions that we have asked. Question number 1 answer, question number 2 answer, and all these answers that we have got. And just now you see that this customer is actually being converted into some X1, X2 up to Xn, this n dimensional vector. And in that n dimensional space, this is actually a point. So essentially what you wanted to know that if this customer, what type of car this customer is going to like, because different customers are going to like different types of car. And then you can see that what type of engine that in which you are interested, what type of speed in which most of the customers are interested, what type of cost which is going to be most attractive to the customers. So these is actually different types of prediction model that you wanted to come up with. And for all of these, you actually either you require the classification, as we just have talked about, or you are interested in regression. So let us also talk about this regression. As you also have said, I missed that. So let us also talk about this regression. Now this, what we wanted to do is that I am having some function. I do not know that what is the value of this function. This function is going to take some x1, x2, and so on, xn. What are these n things? I have customers. All these customers, so many different types of customer, number 1, number 2, number 3, number 4, number 5, number 6. For every customer I have asked a specific set of questions, and this is the answer the customer 1 has given to me, n different answers. I wanted to give this as an input to this algorithm f, that I do not know what it is, but I assume that given such n values, which I am saying that right now is the x, capital X for me, I want to say that there is a relationship between X to Y. What is my Y? Y is my output. And my output here is that if I ask these questions, given this customer, is it going to purchase my car or not? And therefore, Y is going to be yes or no. That's only a binary variable. Or you can say that Y can actually be a probability by which I am saying that this person is going to purchase my car or not. So if this function that we wanted to learn that we do not know, but we assume that it exists, we do not know, but we assume to be that if these questions are properly being designed and answered, this X is going to somehow define or say that whether this X or this person is going to purchase my car or not. So I'm saying that I wanted to learn such a function from this and assume that this function is some theta function. Theta is actually the set of parameters that we are trying to estimate. So this function that we wanted to learn is going to be parameterized over the set of this theta. And if this function is linear function, I am saying that if suppose it's a linear function, then it's going to be of the form theta x1 plus theta 2 x2 and so on, theta n xn, which is going to be equal to some y dash or y that we are actually looking for. So we wanted to somehow come up with this theta. So now you can see that any problem that you wanted to say to be understand the behavior of the customer, maybe it's a classification, maybe it's a regression, can actually be converted into some type of statistical framework, and we then use neural nets. That is the thing that we need to see, that how neural network can be used to solve classification as well as regression type of problems. That's the thing that we are going to see today as well. Anyone else wanted to know?
Sure, thank you. The H1 to Hn here, which you mentioned here,
yes,
is that one question or
no,
set of questions?
Set of questions. So it's set of questions. This X1 is the first answer, first question's answer. X2 is the second question's answer.
Oh, okay. Okay. Thank you.
Okay. Okay.
I have two questions here.
Yes.
So regression is not a type of classification. Regression is nothing but forecasting. Is my assumption correct?
Regression is nothing but
is forecasting. It's sort of
forecasting. Yeah. Yes. Regression and classification, they are two different problems.
Yeah. Now, the other question is, there was one example given by you wherein the usage of neural networks, wherein you said you type in some text and the algorithm will build an image for you.
Yes.
In that, I was wondering if you can explain where does classification fit in?
Yes. So suppose that if I give this image for you, and this image, first of all, there has to be some way by which we can somehow find out that where is this, there is some cat here, there is some dog here, and there is some man here. Suppose that. So suppose that these things are things, and now I want to say that if I give cat and dog sitting with man, so this is the input and this is going to be the output. This is the thing that we are now looking for. So the point here is that first there has to be someone who can classify that there is a cat, there is a dog, and there has to be someone who really understands that there is a clear-cut distinction between man, dog, and cat. So this type of classification networks are actually being used, and they are trying to make different new images which is being conditioned over this text. This text is actually being used as a condition to make such things. To make such images, there has to be someone who can really understand the distinction between drawing a cat, drawing a dog, drawing a man. That's why classification networks, they are also being used at that point of time. So they are being trained initially, some part is being trained as a classification network, and then it's being conditioned over this text.
Got it. Thank you.
Okay. Anyone else who wanted to say anything?
Aditya, the training that you were talking about, is that the data being fed more and more, so the machine applies that same algorithm to identify if it's a right object or not? Is that what you call it as training?
That's perfectly correct. That's perfectly correct. In 2 minutes, let me explain that thing as well. because this course, whenever you ask different questions, I can try to answer them. And because most of the time everything may not be, we can cover in very in great detail. So let us talk about this data. If I have good amount of data, now suppose that this is my good amount of data, I usually divide it into two parts. First is actually called as training, and the second set is actually called as testing. And within this training, I also have a small part that we used to say it as the validation. So given any algorithm A that you want to somehow train, you wanted to train this algorithm A. So you can train it using this data, the training data minus validation point, validation data. You let your algorithm be trained over this, and as you already have said that we have a good amount of such data in which we have the labels of the data, that given this data the correct category is cat, given this data the correct category is dog. So all this data is actually being residing over here. We train over that and test our trained model. Now A, which was previously not trained, now this is a trained model. Given this trained model, if I show it to my validation set, what is the performance? Depending upon my performance, I tune my parameters, the best possible parameters I wanted to come up with. Once I'm ready and I'm performing well over my validation set, I stop training. That is the stopping criteria when you are performing very well over the validation data. And when you are done with this such type of validation data, your model A, which is fully trained, now you show your testing data, report the testing results. That are the result that has to be somehow told, somehow being shown to everyone. So training this data, whatever you are getting the result, that is anyways, because you are seeing that, so you are bound to perform very well over your training data. How well you are performing over the validation set, that is the point. So once you see your performance over the validation set, then you see that I keep on tweaking my parameters, learn new and new parameters in such a way so as to perform as well as possible over my validation data. Once you are done and good and performing well over validation data, then only we will say we will stop our, that's my stopping criteria, and report the results. They are over my testing data. Yes.
Aditya, this is a question related to language.
Language, yes.
Yeah. So do we get any benefit from deep learning? Let's say like currently what I deal with is like how to recognize intent, like when customers are asking for something, we categorize classified things, right? Let's say if somebody is requesting, how do I get access to a printer? So we categorize as, okay, intent is, access. But some people may come and say, how do I print? So they're not using the word access. So classification and recognizing the intent has been a challenge. So does deep learning help in this context?
Yes, perfectly. Deep learning is helping in this context. Not only deep learning is helping, deep learning is creating all the possible benchmarks. And right now it's being breaking all the possible benchmarks in the case of language and linguistic. Let me tell you, recently, if you have heard about that, whatever the things that is being done using G-Talk and whatever the Google machines, they are trying to somehow understand what you are saying, the meaning of that, the semantic of that, the emotion of whatever you are saying, the way in which you are saying, the attitude in which you are saying, everything can actually be extracted from the text, written text, as well as from the speech. So the point is that if you are saying that, and this is actually, as you have said, and because you work in that area, so this is actually a very good problem in which you are asking something and you wanted to know that what is the intent. I guess that it's actually a very good problem, and this in this area, this deep learning algorithm is definitely going to work. And let me tell you that what is that model. The model is going to be recurrent neural networks, as well as the recent upcoming networks that are called as transformer networks. Yes. Can you
So are you
listen?
going to explain about those things?
Yes, definitely. We are going to talk about several of them. We will talk about this recurrent. There's one module that is actually the recurrent neural networks. Is that okay?
Yeah, thanks.
Okay. Anyone else wanted to know anything about this?
So Adit sir, I think whatever the questions, I think we will be covering overall in coming sessions, right? We are going to cover everything.
So whatever the question that you have, don't worry. I mean, you can ask in between. It may be that sometimes I may be able to answer them. Sometimes it may be that it may require lengthy and elaborated answer. So probably I have to somehow, tweak it in some other way, or sometimes it may also be the case that I am not very sure about the answer. So we will somehow see what are the best ways to answer the things. Let us start with the things in which we are interested right now. So a few things that I start with. The first thing that one should have to really understand, which is that if I have a plane like this in which xy and x1 and x2, I am having two things. So actually, as I have said that I have customers, and for each customer I have asked two questions. Question number one, that is actually something, but the answer is actually x1, and then I have asked question number two and the answer is x2. In this way, whatever the data that you have, whatever the customer you have projected that customer into a two-dimensional surface, two-dimensional plane, and in that plane, this is my customer number one, customer number two, customer number three, customer number 4, 5, 6, 7. Similarly, I am having different customers number over here. So I have too many different types of customers, and what is going to happen is that as soon as I ask these two questions, and these two questions that I have asked, if they are asked in a very, designed by an expert, you can easily see that the answer that are being given by these customers are actually being projected into this two-dimensional space of x1 and x2, and they are really separated. And they are separated, why? Because these questions are being very well designed by my expert in such a way so that if you ask these questions, you can easily discriminate between your customers, and you can easily come up with a line like this which can differentiate between both of them. So once you learn such line, you are done. So what is the equation of such a line? I am saying that the equation of such a line is a1 x1 plus a2 x2 is equal to, say, a0. And I wanted to learn. So if I say that somebody has learned this line for me, then it has to tell me three magic numbers. They are a1, a2, and a3. So for any line, if I give you two parameters, you are done. These are also two parameters. You can see it in this way: a1 divided by a0, a2 divided by a0, and 1. These are anyway these three parameters. There are only two parameters for a line. Y is equal to mx plus c, m and c. Either you learn that, or you can learn these three things as well, or you can learn these two things. Everything is equivalent. But if you say that I know such line, then you will have to tell me these three things. So which essentially mean that learning separating hyperplane in this case, which is actually a line, we need to somehow find out a1, a2, and a0, these three things. So if I know these three things, they are actually going to say something about this line, exact equation of this line. And what is the classification function now? If I know this, then what is the classification function? My classification function is going to be, that given any point, say this point is, say, x1, y1, this is, say, x2, y2. Given any such point, what is its class? Suppose that this is my class A. That's the classification that we are trying to do. This is class A. They are good customers. And this is actually class B. They are bad customers. That is actually class B for me. And I have asked and generated these questions in such a way so that I am getting this nice line in between. What is the classification that one can do? So classification means that given this line, I just have to find out that this point is to my left or to my right. If it is to my left, or if it is to my right, that is going to tell me that whether he is a good customer or a bad customer. Which means that if I have the equation of a line, if I have a point, how can I know that whether it is to my left or to my right? What you just have to do is, I am having a1 x1 plus a2 x2 plus a0 equal to 0. That's equation of my line. And suppose that if I say that I am having a point, say xk comma yk, whether it's to my left or to my right, you just have to place it over this line. If you place this point over this line, this is going to be a1 xk plus a2 xk plus a0. If it is equal to 0, it's over the line. If it is positive or negative, that is going to tell you that whether it is to my left or to my right. That is the only thing that one should have to do. What you need to, if I give you a line or the separating hyperplane, you just have to know that the given new point, if it is to my left or to my right, you just have to place over that, and the sign is going to tell you that whether it's to my left or to my right. If you can do that, that is the equation. What we have done over here, we have done it is like a1 x1 plus a2 x2 plus a0 and x0, which is equal to 0. Now assume that x0 is always equal to 1, and if it is the case, then you are only trying to solve ai xi I equal to 0 to 2. And that is the thing that you are saying, that whether this thing is positive or negative is going to tell you that what is the classification thing. The only thing which is now being left, that how to come up with this thing, these magic numbers a1, a2 and a0. And if you can somehow find out these magic numbers a0, a1 and a2, they are going to help you to solve the problem for you. But the point here is that essentially what you are doing, you are trying to somehow find out the best possible a0, a1 and a2 that you can place in your equation like this, and it has to say that for all the points in your training data, suppose that this is your training data, and in that training data you have huge amount of points. All of them are actually customers, and for few of them they are actually good customers, some of them are actually bad customers. So it has to be in such a way so that if I come up with a line like this, then it can differentiate. So you wanted to somehow get the best possible a0, a1 and a2, which when placed here, for all the class A points, they has to be, this line has to say that they are to my left and they are to my right. That is the thing that one should have to really come up and need to solve our a0, a1, a2 in such a way so that you get a line which will differentiate clearly and no point is actually misclassified. This is the thing that we are actually looking for. Now let us see that how such thing can actually be possible for us to solve. So there are two things that one should have to understand before we are going to talk about how we can come up with a classification boundary like this. Let us see, we have a neuron like this. What is a neuron? I'm going to talk about this neuron. So this neuron is actually a summation function. Suppose that if you have inputs like this, here I'm having only two inputs, so let us draw only two inputs for us. Input number 1 is x1, input number 2 is x2, and both of them are connected like this, and both of them are actually having weights associated to it, a1, and the weight here is a2. There is another weight which is also basically they are connected like this. There is another weight which is actually A0, but the corresponding input X0 is always equal to 1. I just have said that. And this neuron, the abstraction of this neuron is that, it's only doing summation over here. This summation is summation AIXI, which means that this neuron is actually an aggregator. And what it is doing, it is aggregating A1, X1, A2, X2, this thing multiplied by this thing multiplied by this, and this thing multiplied by this, and add all of them. A1, X1, A2, X2 plus A0, and it actually says that whether it is positive or negative. You just have to say that if it is positive, I will fire. Fire means that I will say that it's class A, else it is class B. If it is positive, I will say class A, negative class B. I need to learn such A0, A1 and A2 so that for each and every test example, when it's being placed here, because my test example is all the customers that I have and the corresponding X1 and X2 values. So this is my customer number 1. When it go in, when my customer number 1 go in and shown to my neuron, it is going to tell me that whether it is belonging to class A or class B, and there is actually its actual class is class A. If its class is class A, I need that it has to give also every time that it belongs to the class A. And if it is not, then I have to find out that how should I change my weights, how should I change my A0, A1 and A2 so as to accommodate and say that this point is really not B but really a class A point. So for this, we need to somehow come up with a systematic way by which we can learn, by which we can learn these parameters in the best possible way. So this is the thing that in the next 10 to 15 minutes or maybe half an hour, we are going to see that how we can really understand and find out to know the best possible way to estimate these parameters that we are looking for. So
Aditya,
yes.
Sorry, can you go back to your previous slide which you are showing?
Yes.
If you don't mind, where you started this H1A1, can you repeat this 3 minutes or not in one more time?
Yes, I can explain. So what I wanted to say is that, let me rewrite again, don't worry. The point is that this is one neuron for me. What I want is that I have a training data. In training data, I am having these customers. I would like to thank all of you that you are asking questions. I'll be very happy to answer, because if you ask a question, then only I will be in a position to explain each and everything. So feel free every time to ask. Suppose that I'm having I'm having customers like this. Out of them, some of them are actually good customers, and assume that some of them are actually bad customers. I wanted to somehow differentiate between them. So what I have done is that for each and every customer, I took and asked a question, not one, but actually 2 questions, question number 1 and question number 2. This is actually my customer number 1. Again, I have asked question number 1 and question number 2. This is my customer number 2. And this is actually for each and every customer, I have asked this question, and keep on asking all of them. Now, once I ask all of them, first let us see that what is happening. I am projecting all of them into that into that 2-dimensional space, and in that 2-dimensional space, I am actually getting a differentiation between good customer and a bad customer, because my questions are really very good. They are not just their names and their salary, or their name and their demography, or their name and their color. They are useful, really useful question by which they are belonging to this good category and a bad category. Once we understand, let us see that what is the equation of a line. Equation of a line is always equal to y is equal to mx plus c. There are 2 parameters only being there. Let us write it in a way like a1x plus x1 a2 x2 is equal to a0. So which means that this is if I say that I know such line which is differentiating between these 2 things, you mean to say that I know a1, A2 and A0. These three things we need to somehow get best possible A0, A1, A0, A2 and A3. See, this is also a line. If I draw, let me draw this thing. This is also a line, but this is a very poor line for my classification. This is also a very poor line for my classification. This is actually a good line. This is actually a good line. So there are so many good lines out of there. Being classification boundaries which are being there, but see, clearly this is not a good line. This is not a good line. We need to come up with any such line which can differentiate between them. And from initiation, we do not know that what is the best possible value. So if I initially randomly assign A0, A1, A2, you may be having something like this. And from this line, first we need to understand that what is going to happen to my classification. My classification need to say, it's going to say, if I take this line as my classification boundary, it is saying that all of them are actually class B, which is good for all of them, but all of them are misclassified. That's why it's a very poor classification boundary. Then I understand, oh, if I slightly tweak it in this way, still it is very poor. If I slightly, it's slightly better, slightly better, slightly getting better, slightly getting better. Oh, now I'm very good. So in this way, I need to know that how can I tweak my parameters. What are these parameters? A1, A2 and A0. Essentially, there are only two parameters, A1 and A2. We wanted to learn these two parameters and the best possible parameters. Now let us see that what you are trying to learn. What we are trying to learn here is actually just to think about, this is my X1 and X2. That is the feature space. X1 and X2, that's my feature space. Now let us see that this is my A1 and A2. This is my parametric space. Parametric space. In this parametric space, if I take a point like this, what is that? The point over here is actually a line over there. Do you really understand? A point over here is actually a line over there. If I take any point over here, this is actually a line. Why? Because this is A0, this is A0, A1. This is again A1, A2. This is some other A1, A2. This is some other A1, A2. This is some other A1, A2. Different A1, A2s are actually going to say a different types of lines which are being here. Out of all these possible lines, all of them, I wanted to come up with few points. There are only few points which are belonging to some points which are in between this domain, this range, where they are differentiating between the class A and the class B. So we are searching, and we are searching here. We are searching here in this parametric space. We wanted to come up with the best possible A1 and A2 that reduces or gives us the minimum error over my training data. So that is the setup that I have set. This is my setup for you. Now, given this setup, if I say that I only require a specific type of computation, and the abstraction of that computation is my neuron. And what this neuron should have to do, it has to take one X1 and X2, take both of them inside, and it has to learn, by the way, A1 and A2 in such a way so that for each and every customer, if I multiply by this A1 and A2, and there is another input that is A0, and my X0 is equal to always 1, then what I need to do is that summation AI Xi, which means that A1 X1 plus A2 X2 plus X1 X0 is anyways 1, so that's going to be A0. This is the thing. So what this neuron is doing is that it takes this X1 multiplied by this, X2 multiplied by this multiplied by this, and add all these three values. You are going to get a value. You just see that what is the sign of this. If the sign is positive, that is actually class A. Otherwise, that is class B. And what this neuron is actually doing, this neuron is essentially just trying to understand that given this X1 and X2, given this X1, X2 point, the single customer, whether it is to my left of the boundary, which boundary? This boundary, left to this or right to this. If we can understand, that is the classification. then you just have to check that what was its original class and what this neuron is saying. This neuron is actually trying to give you the classification function. Is it okay now?
Yes, Aditya. So going further, will you be showing this in any live example
Yes.
to understand more better?
Yes, yes, it's not done. It's just a very basic intuition. Yes. So now we are going to see. Yes. Now let us see. So now what we are going to see the intuition, and with this actually we can move into the intuition of the neural network. In the next 10 to 15, 30 minutes, we are going to see this intuition and understand how well this type of thing actually works. So I request all of you that in between, if you have any problem, you can ask. Only two things which are required to understand these slides. First one is the very basic of this coordinate geometry and very small amount of probability, very small amount of probability. So we will talk about both of these things, but you just have to be with me. If you have any question in between, please ask as soon as possible. Thank you. So now let us see that this is a neural network that I'm saying that is actually a very scary thing for right now, but assume that, believe me, that it's not even scary. I mean, not that much scary. It's even scarier than this. And this is a very shallow network right now. We right now, it's actually having hidden layer 1, hidden layer 2, hidden layer 3. We used to have 150 layers. We used to have 250 layers. Now you can see that we can even not draw a network like this. But what this neural network is essentially doing, it's trying to solve very complex problem. But at last, what we understand is that this neural network is only trying to solve a problem like this, that a small kid can do, that what are the things which are to my left or to my right. So which essentially we understand that our goal is just only to split the data in the best possible way. So suppose that this is the given scenario in which we have three classes, only two classes, blue class and a red class. Blue class is having 3 points, red class is having 3 points, and you can understand that this is the my initialized line, randomly initialized line, which is not a very good estimate. Why? Because you can see that this point and this point, they are clearly misclassified. I guess that you all understand that we are looking for some boundary like this, which is completely different from the current boundary. But our goal is to come up with a line which can split our data in such a way so that we have class A and class B separated or discriminated. So if I give you a line like this, that I just have shown you, a line like this, it is saying that this point and this point, they are not properly classified. And then you can see that there are two errors, and then you tweak, you try to come up with something like this, then you try to come up with something like this, you tweak it, you started to change your parameters. How many parameters? Right now you are only having 2 parameters. I just have shown you that in 2-dimensional space, you are going to have a line, and line is having 2 parameters. This line is having different set of parameters. This line is having different set of parameters. You tweak, slightly vary your points, slightly vary your parameters of your line, and you keep on tweaking your line in such a way so that your error started to become less as possible. So here it is saying that if you tweak it in such a way, then you are having only 1 error, and then somehow if you slightly change it to this, you are going to have 0 errors. This is the thing that we are looking for. But what is a principled essential way by which we can tweak or change this line? So we will have to understand that there is only one person. So suppose that you wanted to go to somewhere and you wanted to explore in that 2D space. This is my 2D space of parameters I just have shown you. That's my A1, that is my A2, and at any point, this is actually a single line in my feature space. What you wanted to do is that given any new line, which is given any line like A1 and A2, if I give you a line like this, how can I change this line? I wanted to change this line in such a way so as to minimize my error. Now, what is my error? That is the thing that one should have to design. So my error here is number of misclassified point. Misclassified points. If you know that the amount of points which are getting misclassified because of the current line, you wanted to tweak your parameters, both of these parameters, in such a way so that to minimize this number of misclassified points. So how one can do that? And for that, way back, Newton has given an algorithm that is being called as the gradient descent algorithm. Suppose that this is my weight number 1 and that is my weight number 2. What is this weight? And so that's actually the A1 and A2. These are the two parameters. We can give them name weight number 1 and weight number 2. So if you start with some random weight number 1 and weight number 2, Newton has said that first you need to find out that what is your loss or the error that you are seeing, and only one person who can help you to reduce your error, that's your first order derivative. Differentials are the friends. They are actually help you to reduce your error. They used to tell you that, and differential of what? Differential of your loss. Let us draw. Let us write it in this way. That wait. Let us write it in this way. That if I have my loss, if I differentiate this loss with respect to my first weight, and if I differentiate my loss with respect to my second weight, what does it mean? It means that W1, suppose that your W1 is actually a small knob, the type of knob that you have on your radio. So suppose that if you change this W1 in some positive or negative direction, and just wanted to see that what is the effect of rate of change by which I am changing W1, how my loss is changing. And this is the thing that is going to be estimated by this derivative. This is the thing that is going to be estimated by what will happen if I slightly tweak my W2, what is going to happen to my loss. And that is the thing. These are the knobs essentially one should have to tweak, because if you tweak these knobs, what is going to happen? Your line is actually moving. You get another type of line, but you wanted to move into the direction in which your misclassified point is going to be reduced. So I wanted to change my line in such a way so that it always reduce the number of misclassified points, which means that I need to differentiate my loss with respect to my weights. I need to differentiate my loss with respect to my weights. But suppose that if you differentiate that your losses with respect to your weight, then what is going to be the update? How you can update your weights now? So how you can update that is being given by the gradient descent algorithm in Newton's, which means that suppose that you are moving in surface like this and you are here and your derivative is actually in this direction, and you have to move in the just opposite direction. Derivatives are helpful, but in the negative direction. If you move in the negative direction of your derivative, it's definitely going to reduce or minimize the loss. So this is your loss surface. This is your loss surface over which you are running. This is at some point you wanted to know that what is the gradient. It is pointing you in this direction. You move in this direction. Suppose that if you are here, your gradient is in this direction. You need to move in this direction, which means that any Wi has to be modified in such a way. This new Wi should be equal to the old Wi minus the neta times del L by del Wi. This means that I wanted to reduce my loss. So I wanted to see that if I slightly tweak this, how my loss is going to vary. That is actually the derivatives direction. I take the negative direction. And what is this? By the way, this is our learning rate. See, if you are trying to learn, if you are trying to run over here, you should not be very fast. Because if you are very fast, then you will not be able to stop over here. You will lose it and come over here, and you keep on oscillating. So you should not be very fast. There is someone who is saying that, yeah, you are very far and you need to go very fast to this point. If you are very fast, then what will happen? That you will not be able to stop over here. You will shoot it out. You will reach somewhere over here, and then you will need to somehow oscillate like this. That is why it is saying that you need to go, should not be very fast. You use some learning rate which is between 0 and 1. 0 and 1. Most of the time this learning rate is very small, 10 power minus 2 or 10 power minus 3. You will be going very, very slow. And what you need to do, you just have to find out this derivative of loss with respect to the weight that you wanted to update. And you know the previous value because initially you have initialized and then you have got this differential. Just multiply by this and subtract it and done. You have got, so from W1 and W2, that is the initial values, you update them and you will get W1 and W2 after first iteration. And then you again find out the losses and then you again differentiate, again update your weights, and then you will get W1 and W2 weight number after 2 iteration, then after 3 iteration, then after 4 iteration. And the guarantee is that if you are updating it in this way, why your loss is going to be decreased, then you can see that your loss is going to be decreased because you are moving in the opposite direction of your gradient. So it is being said that loss is definitely going to be decreased. That is the Newton's gradient descent algorithm for you. So each and every parameter, whatever you wanted to learn, you initialize it and keep on updating depending upon your losses. The only thing is that you need to know how to differentiate your loss functions. But the problem here is that after explaining all that stuff and nice each and everything, here your loss, as I have said, is that the misclassification, amount of misclassifications that we have, and amount of misclassifications, if I say, so amount of misclassification is, suppose that right now it is 5, then it may be 3, then it may be 2, then it may be 10. So if it is the case, then your loss is somehow going to be decreased, but it is not differentiable because initially it may be 5, then it may be 4, then it may be 2, then it may be 1. If it is going to be reduced like this, it is perfect. It is actually a loss function, but it's not differentiable. How can we somehow make this loss function differentiable? Because it's a discrete function, it's not a smooth function. This is actually a differentiate, it's actually a discontinuous function because there is nothing in between 5 to 4, nothing in between 4 to 2, 4 to 3. There is not something like 4.5. There is not something which is 3.2. This is actually a discrete function for us. So how to come up with a loss function which is not discrete in nature? That is actually logistic regression. In this logistic regression, if we let us all of you to understand, it actually says that previously each and every point, if it got misclassified, I am saying that total number of misclassified, each and every point is being treated in the same way. If it is classified, no penalty. If it is misclassified, 1 penalty. Right now I am saying that each and every point is now going to have a penalty. Each point have a penalty. It's very arbit thing that even if you are correctly classified, you are going to get a penalty. Previously, if you are correctly classified, you are not being counted at all. You are only counted if you are misclassified. Right now I am saying that even if you are correctly classified, I am going to give you a penalty, but the penalty will be small. If you are misclassified, you are going to get a penalty, but the penalty is going to be very high. If that is the case, then now you can see that with respect to this line, you are going to have error like this. 4 small errors, 2 big errors, and ultimately what is going to happen, that then you change your line and now you see that every point is going to have an error. And what is the error? You can say that how far you are from the line, how far you are from the line, how far you are from the line. So if you are in the correct zone and misclassified, 1 by the distance, because it's inversely proportional to the distance you are from the line, because you are in the correct zone. If you are in the incorrect zone, how far you are from the line. So we can add and find out that how far you are from the line, and you can easily come up with a loss function which will say that if I add all of them, then we wanted to minimize. Suppose that right now there are only 2 points which are misclassified, so you are getting certain amount of error. Right now I change it, and when I change it, now you see that this was the initial case when 2 points were having more error. Now every point is less. So we are actually minimizing this error. Instead of minimizing the that's called a misclassification, we are minimizing this. That's actually being called as the logistic regression. Only thing which is now being left is that if we, how to come up with an error function like this, which is saying that if you are misclassified, error is more. If you are correctly classified, the error is less. This is the thing that we have to somehow define, that what is our loss function. One such loss function we are going to derive right now. But if we have such loss function, you just have to do what? That's actually called as gradient descent. I just have talked that out of all possible directions in which you wanted to go, you are only going to choose that direction which is going to reduce your height. That is called as gradient descent over here, and the analogous version can be actually seen over here, in which the person is taking a path. Accordingly, the line is being tweaked and changed in such a way so that soon you will see that the different misclassifieds are now being converted into the correctly classified points, and at some point of time this guy is also coming down, and you are also going to get the best possible estimate of the classification boundary that you was looking for. So now you see that you have got a good function like this, and this guy also came down. Yes, somebody want to say anything?
I have a question.
Yes.
In the equation that you showed
Yes.
previous slide, you said the neta was learning rate and it's between 0 1.
Yes.
My question is, why can't you have the neta closest to 0 such that you can minimize error?
Yes.
Like let's say
correct.
like 10 to negative 6 or 10 to negative 8. Why can't you have that?
Yes. So the point is that neta is actually the learning rate, and it is that if your direction is this, we need to go in this direction. The point is that we are going in the negative direction. This is okay, but if you are very fast while going fast, means that if you take the full derivative without this neta, or neta is equal to 1 or very close to 1, then you are going to update your wi's very fast, because your wi update is going to be wi minus del l by del wi. This is a very fast update. If you update very fast, it's almost like that you wanted to drive in a valley and you are very fast. So actually your answer is over here, not here. So if you are very fast, then you will be fast and fast and fast. You keep on getting yourself very fast, and you will not be able to stop over here, because suppose that you are here, you take an update and it will take you here. So you keep on oscillating. At this point, it will be very difficult for you to stop here, because in the next step, it will take you over here. From here, next step, it will take you over here. So you will be oscillating in between. That is why it's being said that you keep on reducing your speed when you are reaching towards the minima. Is that okay?
Yeah, that's fine. But I was just wondering, so then why can't you just take limit to 0 for that? So if you don't want to go so fast, why can't neta be the closest to 0 as possible?
Oh, that's very good. So let us understand it another way. That suppose that I have shown you a very nice and simple and easy surface. Right now, assume that you are at mountains, and something like this is going to happen. Let me draw a surface for you, and then probably you may be able to understand. So suppose that our surface is something like this, and at this place, you may be slightly fast, you can be slightly fast, but this place you should not be very fast, because it's going to be very easily you will be taken out of this. So the point is that it depends upon the surface over which you are actually trying to run. Now if your gradient at the surface is very high, you should not be walking very fast. If your surface is very low, if your surface is almost like this, then here almost there is no derivative, and it is very difficult for you to move. So probably you require more neta to somehow change and move as fast as possible to cover this thing. And then Niagara Falls comes, and then what happens that your speed becomes very fast. So you should not want your speed to be very fast when you are moving in some places where the descent is very steep. So that is why this learning rate is actually being said very small, but this learning rate is actually being not being fixed. In next upcoming slides, or maybe at some point of time, I can tell you that adaptive learning rates are actually being used. They are not being fixed to one value, but depends upon the gradient that you are seeing, what the gradients that you are having. These gradients are going to tell you that how fast you should be walking. Is that okay?
Yeah, that's good. Thank you.
Okay.
And how would you determine the gradient?
So gradient is just a function. So you have got a loss function. Depending upon your loss, you just have to differentiate that loss function with respect to your weight vector. See, loss function is, suppose that your loss function is, say, let us write it in this way. My loss function is y minus x square. And I wanted to differentiate it with respect to x. Then it is going to be 2y minus x. So that's the loss function, that's the derivative of this with respect to x. So if you wanted to change your x in such a way, then your new x is going to be x minus neta times bracket 2y minus x. That is the update rule for this x.
Okay, so the first derivative of the function will let you know the gradient.
Definitely, yes. Yes.
Okay.
Okay.
Thank you.
Yes. So we are done with this. So what we are going to do is that so I have said that I want an error function that can be differentiable, because most of the error functions are not differentiable. We wanted to come up with an error function which is differentiable. How we can come up with such function which is differentiable? That is the thing that we will have to somehow look for. So if I give you, that is the thing that we are trying to see. So if I give you, I don't know how much time is left. Yeah, we have 15 minutes. So what we need to do is that, given as soon as, so remember what we are going to do. We are going to come up with a error function, and that error function is in terms of probability. Let us see how we can move up to that. So if I give you a 2D space like this, all of this is actually a 2D space for me. Within this 2D space, as soon as I give you a line like this is actually a 50-50 line. 50-50 line means that this is actually a classification boundary. And as soon as I have given you a classification like this, it is saying that whatever the points which are over here, we are not sure, they are 50-50, maybe belonging to the blue class, maybe belonging to the red class. Then as soon as you go as far from here, this is very likely to be blue, this is likely to be blue, this is likely to be red, and this is very likely to be red. So as soon as I have given you a line, I have not only given you these two set of regions, that this region belongs to blue, this region belongs to red. I have actually given you the full probability density function, which means that if you give me any point, whether it exists or not in your data set, if you give me any point, I can tell you that whether it is blue or it is red, as well as I can tell you that with what probability it is blue or red. If I say that with 0.4 probability it is blue, which means that with 0.6 probability it is red. How? It is that because you can see here that how far it is from the boundary. So if it is, say, this much far, then you will say that it is likely to be blue. If it is here, it is very likely to be blue. If it is here, it is very, very likely to be blue. If it is here, it is likely to be red. If it is here, it is very likely to be red. It is very, very, very likely to be red. So which essentially mean that we are talking like some surface which is discretized in such a way so that I am having parallel lines like this. And for all the lines in between any point, I can say, you just give me any point. If it is belonging to this zone, I am going to give some value, some probability, some other probability, some other probability. And what I'm saying, my probability of being blue, I am saying. So here it is very high, here it is slightly less, here it is, so here I can say 0.9, here it is 0.8, here it is 0.7, here it is 0.6, this is 0.5, this is 0.4, this is 0.3, 2, and 1. So actually you have got, for now you give me any point, this I'll say 0.8, this is 0.6, 0.7, this is 0.6. with 0.6 probability, it is actually blue. So if I give you a line, I have give you actually the full probability density function that you give me any point, I am giving you what by what probability it is blue. 1 minus of that is actually by what probability it is red or belonging to some other class. Now just to see that you really want a probability density function like that, like this, or you are interested in a probability density function which is like this. So my point is that let us understand it in this way, that this is my decision boundary first of all. Secondly, I am saying that probability, so if I give these values, they are not definitely going to work because they are not in between 0 and 1. So first thing is that everything which is over here, it has to be 0.5. These things has to be 0.6. But the only thing that I have changed here and my previous boundary was that if it is with this boundary is actually saying that this is our decision boundary. And decision boundary, if you go slightly far from this, now assume that this is India-Pakistan boundary. And I'm talking about the amount of risk of our life. Risk of life. Now, risk of life is not linearly weighing. Risk of life is exponentially changing here, what you can see. Why? Because if you move 2 kilometers, the probability is being changed. If you move, risk of life is actually being changed. If you move 3 kilometers, if you move 5 kilometers, if you move 8 kilometers, now your probability or the risk of life or being a blue is actually being incremented significantly by 0.1. And now this was actually Jammu and Kashmir in India. So now you see that if you move very far from it, now you are entering in the Uttar Pradesh. Now here, if you move only 10 kilometers, nothing is going to happen. If you move 20 kilometers, nothing is going to happen. 30 kilometers, nothing is going to happen. Maybe at this point of time, probably you may be having value 0.5. But this is actually South India. Here you move, huge amount of distance. The risk of life is not going to change with respect to the India and Pakistan boundary. If you are just to think about that, if you move 2 kilometers inside the LOC, just 2 kilometers inside the LOC, the risk is continuously being changed and exponentially it's actually being changed. So that is the point, that we are not actually looking to have a function like this, which is linearly reducing or coming up with the probability density function which is linear. We are interested in a function like this, which is giving more and more importance to these guys. Why? Because these guys, these points, the points which are going to be here, they are the ambiguous points. With respect to this given line, these points are going to be the most ambiguous points, and they may either belong to class A and class B. Our classifier may not be very good with them, but our classifier is definite about them. It's saying that this is blue and this is red. We do not have any doubt. And as far as you go from our decision boundary, we can easily differentiate. These are the hard samples that we are going to get. These are the customers that you are not sure that whether they are going to repay your loan or not. They are good or bad. They are actually intermingled. But these guys, they are really good. They are really bad, whatever. So what is this? This is actually that from here we wanted to go to there. What is a function that will take something like this and convert it into this? That's actually a squashing function. First of all, squashing functions are those functions which will take anything in your number line. Full number line is here. It will take anything in your number line and convert it between 0 and 1. That's first thing. Second thing is that if you are, no matter how big you are, everything is being converted into here. Why? Because we are almost certain about them. We are almost certain about you guys. We are only interested to give more and more weightage to them. Why? Because they are in the ambiguous zone. 0 is going to be mapped to 0.5. And now everything is between 0 and 1. That is, now it can actually be seen as a probability. First of all, 0 is being mapped to 0.5. All those things which are in between, they are taking the center stage most of the time. All the my values are being over here. All of them, they are not given much importance. Why? Because they are easy samples. They are easily being solved. We do not have much problems to differentiate between them. Most of the problem is going to happen with these type of guy. One such function which will take the full number line, converted into 0 and 1, is called as sigmoid. That's also being called as the activation function that we are interested in, which is 1 divided by 1 plus e power minus of x. This is our activation function. So if I take something like this and apply activation function over that, we will convert our probability map from here to here. Now in 5 to 8 minutes, I mean, next maybe 3 to 4 minutes, I require your attention again, that now if I give you these set of points, this is belonging to class 1, class 2, and class 2. These are the 2 different classes that we have. Now what I wanted to say is that if I give you a line like this, which means that I am giving you a line, you can relate with this, that given this line, we are having an exact probability density function. I just have shown you this is a complete probability density function. So you just have to give me the line. I know that what is the probability density function with respect to this. I find out that with what probability this point is red, with what probability this point is red, with what probability this point is red, 1 minus of that is going to with what probability this point is blue, and with what probability this point is blue. With respect to this given line, we can find out what are the probabilities that this point belongs to its correct class, this point belongs to its correct class, this point belongs to its correct class, and this point is also belonging to its correct class. Basically, all of them are belonging to their correct classes. I wanted to find out that what is that probability, and this probability is definitely with respect to this line, this probability is going to be very low, this probability is going to be very high, this probability is going to be low, and this probability is going to be very high, because this is misclassified and this is misclassified. This is my blue zone and that is my red zone. So suppose that I have got that with what probability this is blue, sorry, with what probability this is red, this is blue, and this is blue. I multiply all of them, and all of them are actually the independent events. Then the joint probability means that what is the probability that all of the points are belonging to their correct class. That is the joint probability. I multiply all of them, and this is actually called as the likelihood. So what is the likelihood? Likelihood is that given a line, given such points, we wanted to know that what is the probability that all of them belonging to their correct classes. And once I got this likelihood, I wanted to maximize this likelihood. I wanted to maximize this likelihood by adjusting my line in such a way so that my likelihood got maximized. I need to maximize that. But the point again that you have got a loss function. This is my loss function, but loss function has to be additive for each of my points. But here it is multiplicative. We do not work on the multiplicative type of loss functions. So what one can do is that first simple thing is that anything which is being seen as a multiplication, if you apply log of that, multiplication is directly being converted into addition. So first thing is that we will be working on the probabilities, but we will not only be working in the probabilities, we will be trying to first of all maximizing the likelihood. We understand that if this is the line, then my likelihood now got maximized. Why? Because all of them are actually belonging to their correct zone. So my likelihood got maximized, but we will not be working on likelihood. We will apply log over that. Why? Because we wanted to see everything in terms of addition. So we will be working on log likelihoods. But if I take a value which is between 0 and 1 and take a log of that, log becomes negative. That is why we will be using the negative log likelihood. And here we were maximizing the likelihood. Now we wanted to minimize the log likelihood. That is why we use minimization of the log likelihood. So now you can see that given a line like this, given points like this, given points like this, let me use this, given points like this, I first of all find out their probability, then take the log of that, and then take the negative of that. I find out the probability of being this point as blue, take the log of that and negative of that, blue, log of that, negative of that, and add all of them. That is the log likelihood for me for such a scenario. You can see that this such scenario is not a very good scenario. Now let us see that if I take this line, I find out with what probability with respect to this line, this is blue, this is blue, this is red, and this is red. Then take the log of that and then take the negative of that and then add all of them. This is, now you see that log likelihood got minimized. Given a log likelihood type of thing, how we can play around, I just have shown it to you. So this is our function, this is our loss function, which means that if you have a line, I will take the probability, I will take the log of that, and I will take minus of that, and that is my loss function. By the way, what this loss function is ensuring? This is ensuring that if you are misclassified, then you will be given more penalty. If you are correctly classified, you will be given less penalty, and that is the logistic regression loss function for us. With this, in 2 minutes to 5 minutes, we are going to finish the session, in which few things we just have to see. So if you are ready, then I have to relate everything to neural networks. So in 5 minutes maximum, I just require your attention. Here, now just see that we have seen this thing, that this is my single neuron, and you all understand that I have X, I have Y. This is actually my two-dimensional space, in which I am having a line, in which I am having multiple set of points like this. And somebody has given me this line equation. This line equation is 2x plus 7y, which is equal to 4. So if you wanted to do a classification and use your neuron to do the thing, then you set your this weight as 2 and this weight as 7, and take any point. You take this point, place it over here. It will give me the corresponding X is going here, the corresponding Y is going there, and once you apply, you are going to get 2x plus 7y. This 4 is going to tell you whether it is more than 4 or less than 4. That is actually being called as the bias of a neuron. Or if you remember, this is A1, this is A2, or you say this is weight number 1, weight number 2, and this is A0 or W0. This guy is doing what? This guy is doing summation AI xi I equal to 1 to I equal to 0 to 2. And just we want to see that what is happening. So one neuron is doing classification for all of the points. You take this point and take the X and feed it over here, the Y feed it over here. It is going to tell that whether it is firing or not. Basically, what is the sign, whether it is positive or negative, and that is going to tell you that whether it is belonging to the class A or class B. But most of the time, what is going to happen, that one neuron can learn only one line. But most of the time, your points are not going to be linearly separable. Now you can see that you cannot come up with a single line that can solve your problem. You cannot come up with a single line. Whatever the line you draw, you are going to have huge amount of losses. So single line is not going to solve. But if there is someone who can solve it like this, non-linear regions like this, then you are happy. So if that is the case, non-linear regions, how we can use this neural network, because neural network can only learn boundaries like this and can solve the problem for us. How I can relate that we can learn complex non-linear boundaries, because these are the things, this is our business in which we wanted to work on. Most of the time our boundaries are not going to be linear, they are going to be non-linear. So let us see that how we can do that. It's actually being seen as combination of two such boundaries. Suppose that I have neuron number 1, which is trying to learn this hyperplane. If I have a neuron here which is trying to learn this hyperplane, I have two neurons and they can learn two hyperplanes. Now I wanted to somehow combine both of these neurons learning so as to come up with the best possible boundary like this, that the non-linear boundary like this. How it can be done? So just you see that we wanted to merge. So we started to merge this region and this region. It's just an animation, because of that it's showing like this. But if you can see in between, that ye are going to have something like this. I take this and merge both of them in such a way so that I can get a non-linear boundary like this. Suppose that if I give more weightage to, so if I give equal weightage to both of them, weight number 1 to this and weight number 2 to this, maybe 0.5 and 0.5 to both of them, then probably I may end up something like this. But suppose that if I give more weightage to this guy, more weightage to this guy, less weightage to this guy, maybe say 0.7 to this and 0.3 to this, then what will happen? That the boundary that you are going to get may be more inclined to this. If you give more weightage to this, then your boundary is going to be more inclined to this. If you give same weightage to both of them are going to get something like this. What does it mean really is, that if I take this, merging or joining both of them is going to give me some non-linear boundary like this. What is the meaning of merging two neurons boundary is actually, let us see it in this way, that suppose that I have a line like this and I have a line like this. With respect to this line, I wanted to merge this point over here. So if I merge this point over here, then 0.7 is the probability by which it was blue with respect to this line, and with respect to this line, assume that the probability by which it was blue, that was 0.8. If I add both of them, that is actually the meaning of merging. You take the decision that is being given by the neuron number 1 or the hyperplane or the line number 1, that was 0.7, and this is 0.8. You add both of them. You are adding two probabilities. You are going to get a value which is related to the probability, but it's not actually the probability, because if you add two probabilities, P1 plus P2, the value becomes more than 1. So again, you apply a squashing function which will take anything and convert it between 0 and 1. So again, over this we will apply the squashing function. So that is the thing. How you are merging any point? You take this point, you take this point with respect to this line, find out the probability, with respect to this line, find out the probability, add both of them, apply sigmoid over that. That is the meaning of merging two regions, merging the decisions or the responses of two neurons. So now you can see that, as I also have said, that if you give same weightage or if you give different weightage, that is the thing it actually wanted to say. And if you give different weightage, then what will happen? This has got more weightage, this has got less weightage. So the final boundary is going to be much more dependent upon, looks similar to the upper thing. Combining two regions definitely is going to give you two different type of outputs. So that is the thing, that assuming, let us see that assuming, I just have to rush through. Yes. So assuming that I am giving 7 weightage to this guy, 5 weightage to this guy, and here the bias of this neuron is 0.6, which means that whatever the thing that you are going to get over here, I am going to multiply by 7. Here, whatever the thing that you are going to give me, I am going to multiply it by 5. That is the way by which I am giving more weightage to the upper guy, less weightage to this guy. So now you see that 7 multiplied by this. So previously we were adding directly. Now I am adding with the added multiplication. Whatever the value that you will get, I apply sigmoid or I apply the activation function over this. Now this, what is happening inside is that this thing can actually be seen as a network like this. This thing can actually be, so this whole thing is can actually be seen as a network like this, which is saying that whatever you are going to give me over here, that is going to be multiplied by 7. Whatever you are going to get from here, that is going to be multiplied by 5. And -6 is the bias, which is just only telling us whether the addition of both of these things is going to be more than this threshold or less than this threshold. That is the third value. So this is actually learning one hyperplane. This is learning one hyperplane, and this is actually merging these two hyperplanes by understanding and learning the weights by which I should be merging these two hyperplanes so as to get the best possible non-linear boundary that one can get. So now you see that this is also trying to learn a hyperplane, but in this hyperplane here can actually be seen as a non-linear boundary. So in our final discussion, I can show you that this is the first network or the first neuron which is trying to learn these things. This is my second neuron which is trying to learn this line, this is trying to learn this line, this is trying to learn this line. So that is why this line is 5x minus 2y minus 8 equal to 0. This is 7x minus 3y equal to minus 1 equal to 0. And both of these guys are learning this. And by the way, the third guy, it was actually trying to learn how I can merge these two things. The decision that I have got from this, the decision that I have got from this, how I am merging. You take both of them, and now you can see that this is nothing but in the merger like this. So both of these things come close to each other, and this is the single. So that is actually now what you have got, x, y, same x, y. So you can have, x and y, forget about this thing. This x is going here, this x is also going here, this y is going here, and this y is also going here. The same thing is being happening when you can see here. So this is my x, this is my y, x is going to be here, and here also, y is also going to be there, and here also. This neuron is learning this type of hyperplane, this neuron is learning this type of hyperplane, and this neuron is, by the way, trying to learn this type of boundary. So this is actually called as the in-between intermediate hidden layer. This is my hidden layer, in between hidden layer. This is my output layer, because that's only directly going to give me the output. So now you can see that my input layer, I am having my x, I am having my y, and this is my hidden layer, which is in between. It's trying to learn two hyperplanes, and later we are merging them in such a way so as to get the non-linear boundaries in which we are interested. If I have more hidden layers, instead of only one such line, if I learn 3 such lines, then I can learn something which is very non-trivial. It's actually like a triangle. It's a completely confined thing, and a single hyperplane or a linear boundary cannot never be able to estimate so closely. If I have, instead of having 2-dimensional input, if I have 3-dimensional input, then instead of having the lines, we are going to get the hyperplanes. So we are going to get planes for the hidden layer and the output layers, because these planes, when they got merged, you are going to get surfaces like this, complex surfaces like this. Now see that instead of having one hidden layer, if I have 2 hidden layers, what you can learn is something really amazing. You have here, you are learning 2 lines. Here you are learning, first neuron is learning how to merge this and this. So once you merge this and this, you can learn something like this. You can, the second neuron in the second hidden layer is actually learning how can I merge this and this. Same thing. It will learn something which is completely different from the above thing. When you merge both of them, this neuron is learning something even non-trivial. And the non-linear boundary this neuron has learned is something really amazing. You can see that how precisely it has moved inside and can go out. It's almost like a surgical strike that's actually being happen. You move inside the other territory without any casualty, come back. And this is very difficult to, learn by a single neuron. So this is the thing that I wanted to somehow add to show you that if you add more and more hidden layers, what will happen? If you add more and more neurons to a hidden layer, what will happen? And if you have more and more deeper structures, deep neural network, that is why it becomes, more and more deep. If it is very deep, then such deep networks are going to learn some non-trivial boundaries, and you can get this such complex boundaries classification possible for you. You can ask any question if you want. I'm done.
If anybody has question, please feel free to ask, or you can note also. So tomorrow, before we start the session, Aditya sir can help to answer those questions.
Yes, tomorrow we can answer if you have any other thing. Meanwhile, I will share these slides as well, or I guess that it's being recorded. It's going to be shown to them, or
yes,
what is
yes,
the
Aditya
way?
sir.
Yeah, then it's okay. Then I think that you do not require the slides. It's anyways available. Is this okay?
Yes, I think it's good. Just still trying to understand the last piece that you went through. So anyway, I'll just review the recording.
Yes, yes. So view the recording, and tomorrow again you can ask Vijay anything that you want to know.
Okay, sounds good. Yeah. Thanks.
Okay, thank you.
All the participants, you will be like on your dashboard, you will be able to see the recorded session, today's recorded session.
Okay.
Also from Infini, we will be sending a feedback form. You can definitely fill it and send it back to us. And tomorrow we will have the second session in the same time that is we had today. And if you have any questions, you can send it to us through email.
Aditya, is there something we need to come with preparation before any class, like any
See,
basic?
any preparation, not much. My only point is that sometimes what happen that if you are not able to understand, you can ask. That is the only preparation I feel that if you do, then we are done. Because see, I know that stuff, but I also understand that this is the first time that you people are going to listen this is stuff. So several times things become slightly complex. Then you can ask. I can somehow reduce the complexity. And mostly what happened that after the class probably you can spend time to understand the stuff. During the class I will let you understand somehow the concept, but after the class I request all of you to please go and try to listen to this concept again, and wherever you feel any problem or difficulty in the next when I start, please ask those things again. I will refine them.
Sure. So at least my suggestion is
Yeah.
before going more deep into deep learning. So if you can show us one real-time example of how this technology or this subject can be used, so then it will be easy for us to digest, because it's a bit hard to digest this information. So
Yes. So if I clearly understand, you want to see some demo or application. Can you elaborate? I can try to produce. Please give some slightly elaborate.
Correct. So for example, I remember earlier in our one of our session, what we saw was like how a taxi driver who is associated with Ola or Uber knows where to go, be ready at a point so that he will definitely get a ride request. So I'm just giving an example. So how the data input data can be given to a algorithm, and it is telling you at which point to be. For example, at morning 9 o'clock, be near airport, so you will definitely get a ride request, right?
Okay.
So I'm just giving an example. So let that any real-time example. So it will help us to understand when we learn this, how we can utilize this to our existing domain where we work, or in our daily world where we can apply this algorithms or machine learning, where we can do some like. I know you showed us customer C1, C2, this one.
Yes.
At that time, I am able to remember, but once you go again deep, I'm not able to remember what is C1, what is C2, what is A1, what is A2 here. So
okay.
Maybe it's taking time for me to digest, but just this is my feedback. Like,
yeah, I will try to do that in the next class. First, I will do that, and then we will see the other thing.
Sure. So it will help us. We know that over the next few classes, this is where we are going to go there. So thank you.
Okay.
And tomorrow, what we are going to cover, Adit sir?
Tomorrow we are going to cover this fully connected networks as well. So some intuition I have said, and according to that, we will see that how these fully connected networks are being designed and trained. We will also have to see that what do I mean by different types of loss functions, what different types of activation functions, and then probably what different types of optimizers which are there, which can help us to really drive in that high dimensional space of parameters in the best possible way. These are the things that we are going to see.
Okay.
This schedule, I guess it's being shared. We have made one such schedule. So similar to that, we are going to,
Yeah, I think it has been shared with participants.
Okay.
So if there is no question, thank you so much, everybody,
Yeah.
Thank you so much, Adit sir, for this wonderful
Thank
session.
you. Okay.
Thank you.
Hello. Thank you. It was wonderful.
Somebody want to say anything?
Just
No,
want to
sir.
say it was really good. Thank you.
Yes, Sylvia, do you want to ask any question?
No, I think they are fine.
No, that's okay. Then okay, bye. Good night. Good night.
Bye.
Bye bye.